Hello Calc 3 and welcome back to another video. In this video we'll be covering section 14.6 on tangent planes and differentials. So let's get started. Remember from Calculus 1 that the tangent line to a curve in the plane gave us a linear approximation of the function at a point. So I have a function in green which I've drawn in the plane here, and then we can pick some arbitrary point x naught and the corresponding point on the curve, and we can also draw a line tangent to that point or tangent to the curve through that point, and we can use that tangent line to approximate the value of the function at x values that are close to the point x naught. So if we pick some other x value, say x naught plus delta x, maybe somewhere over here, then the value of the function at that point is going to be this y value here, where I've just drawn the red dot, but the tangent line approximation for the function at that point is going to be this blue dot here. And you can see that as we get closer and closer to the point x naught that describes our tangent line, this approximation gets better and better. Well, in this section, we're going to use the gradient vector, which we defined in the last section, section 14.5, to define a tangent plane as opposed to a tangent line to a surface given by some constant is equal to f of x, y, z, so some level surface. We then use the tangent plane to approximate the function near a particular point. Okay, so let's develop the notion of a tangent plane and also normal lines. So at the end of last section, we found that if I have a curve r in space, and it's in particular a smooth curve, and it goes on a level surface, f of x, y, z is equal to some constant c, then the derivative with respect to t of f of r of t, where again r of t is my curve, is equal to the gradient of f of r of t dot product with r prime of t. So again, we developed that at the end of section 14.5, and since f of r of t is going to be equal to that constant c by assumption, the derivative of f of r of t is going to equal 0. And this implies that the gradient of f of r of t and r prime of t are going to be orthogonal at all points on this level surface, f of x, y, z is equal to c. So again, we developed all of these facts at the end of the last video. And now, if we consider one point p naught on the level surface, all of the velocity vectors at p naught, so all of the velocity vectors that are going through p naught, are orthogonal to the gradient vector at p naught. So all of the tangent lines lie in the plane that passes through the point p naught and is also normal to the gradient vector. So remember from chapter 12 that to write down the equation for a plane, we needed a point in the plane and we also needed a vector that was normal to the plane. Well, now we have both of those pieces of information here. We have our point p naught on the level surface, and that will be inside of the tangent plane, and we also have that the gradient vector is going to be normal to the tangent plane. So here we can define what the tangent plane is. So the tangent plane at the point p naught on the level surface f of x, y, z is equal to c of some differentiable function f is the plane through the point p naught that is normal to the gradient vector at the point p naught. And the normal line of the surface at p naught is the line that passes through the point p naught and is parallel to the gradient vector at p naught. So here we have the definition of the tangent plane and the normal line. And using that definition, we can immediately write down equations for both of these things here. So the tangent plane to f of x, y, z is equal to c, some level surface, at the point p naught is defined to be the partial derivative with respect to x at p naught times x minus x naught plus the partial derivative with respect to y at p naught times y minus y naught plus the partial derivative with respect to z at p naught times z minus z naught is all equal to 0. And here we're just using the equation for the plane that we developed in chapter 12, where the fact that we have each of these partial derivatives multiplying x minus x naught, y minus y naught, etc., is because the gradient vector is going to be the vector normal to our plane. So this is the I component of the gradient vector, the j component of the gradient vector, and the k component of the gradient vector. And the normal line to f of x, y, z is equal to c at the point p naught is given by the following parametric equations. So we have x is equal to x naught plus partial x at p naught times t, y is equal to y naught plus partial y at p naught times t, and then z is analogous. So here, again, we're using the equation for the line that we developed in chapter 12. So x naught, y naught, and z naught are coming from our point p naught, and then we know that the normal line is going to be parallel to the gradient vector, which is where each of these terms is coming from, multiplying t. So let's give an example where we find equations for the tangent plane as well as the normal line. So here we want to find the tangent plane and normal line of the level surface f of x, y, z is equal to x squared plus y squared plus z minus 9 is equal to 0 at the point p naught is 1, 2, 4. So again, this level surface x squared plus y squared plus z minus 9 is equal to 0 defines some surface in three-dimensional space. We want to find the tangent plane and the normal line. So to do so, we're going to use the definitions that we have from above. So the gradient of f is going to equal the partial derivative with respect to x in the I component, partial derivative with respect to y in the j component, and partial derivative with respect to z in the k component. And you can calculate and find that this gives us the vector 2x, 2y, 1. And then we can evaluate the gradient specifically at our point p naught, so the point 1, 2, 4. So we plug in 1 for x, 2 for y, and 4 for z, and we get the vector 2, 4, 1. And now using this fact, we can just write down equations for the tangent plane as well as the normal line. So the tangent plane is 2 times x minus 1 plus 4 times y minus 2 plus z minus 4 is equal to 0, where each of these components from the gradient is multiplying x minus x naught, y minus y naught, and z minus z naught. And then we also have our parametric equations for the normal line. So we have x is equal to 1 plus 2t, y is equal to 2 plus 4t, and z is equal to 4 plus t, where these values correspond to our point p naught, and then the coefficients multiplying t correspond to the gradient vector at the point 1, 2, 4. Okay, so let's say that instead of a level surface, c equals f of x, y, z in space, we have a surface given by z is equal to f of x, y. So now we have a function in two variables that gives us our third coordinate z. Well, we can manipulate that equation. So z is equal to f of x, y implies that 0 is equal to f of x, y minus z. And at this point, we can just use information that we've developed in the previous section here. So once we have it in the form 0 is equal to f of x, y minus z, then the right side of this equation becomes a function in three variables. So we'll call that big F of x, y, z. And now big F of x, y, z is going to equal 0. So I have that written down here. And at this point, we just have a level curve for a function, or a level surface, I should say, for a function in three variables. And again, this allows us to apply things that we already know. So the gradient of big F is going to be partial x, partial y, and partial z. And we can find that those are equal to the partial derivative of little f with respect to x, the partial derivative of little f with respect to y, and then minus 1 as the k component. So that minus 1 is coming from the fact that when we take the partial derivative of big F with respect to z, all of this function little f of xy is going to go to 0, and we're just left with this minus z, and when we take the derivative of minus z, we get minus 1. Okay, and this allows us to say or develop an equation for the plane tangent to the surface z equals f of xy at the point x naught, y naught, f of x naught, y naught. So the plane tangent to the surface z equals f of xy of a differentiable function f at the point p naught is x naught, y naught, z naught, which in this case is equal to the point x naught, y naught, f of x naught, y naught, is given by partial x of x naught, y naught times x minus x naught plus partial y at x naught, y naught times y minus y naught minus z naught is all equal to 0. So nothing too foreign is happening here. We're just taking this gradient that we developed above, and we're using that as the normal vector to our tangent plane, and that's where each of these values is coming from. And here we have this minus 1 out in front of z minus z naught. And just like the equation before, we still use x minus x naught, y minus y naught, and z minus z naught. All right, so let's give an example of this here. So we have our function xyz is equal to x squared plus y squared minus 2 is equal to 0. This is a cylinder, and g of xyz is equal to x plus z minus 4 is equal to 0. So this is some plane in space, and both of these functions are going to intersect at an ellipse, E. And we want to find parametric equations for the line that is tangent to our ellipse E at the point 1, 1, 3. Okay, so let's get into this problem. This is somewhat involved. So we know that the tangent line for this, this intersecting ellipse is going to be orthogonal to both the gradient of f and the gradient of g at the point 1, 1, 3. And it will therefore be parallel to the cross product of the gradient at, or the gradient of f at 1, 1, 3 and the gradient of g at 1, 1, 3. So first we find the gradient of f. So we take partial x, partial y, and partial z in the respective components, and we end up with the vector 2x, 2y, 0, and then the gradient of g. Again, we take partial x, partial y, and partial z in the respective components. We end up with 1, 0, 1 as the vector. And now we can take both of these gradients and evaluate them at the point 1, 1, 3. So when we plug in for the gradient of f, we get the vector 2, 2, 0. And when we plug in for the gradient of g, we get the vector 1, 0, 1. And now we can take the cross product of both of these vectors that we just found. So we take the cross product of 2, 2, 0 and 1, 0, 1 by calculating the determinant of this matrix here. And hopefully at this point you're comfortable with calculating the cross product. Ultimately, we find that the cross product is equal to the vector 2i minus 2j minus 2k. And so now we have a vector that is parallel to the tangent line going through our point 1, 1, 3. And so we finally have enough information to write down parametric equations for our tangent line. The parametric equations will be given by x is equal to 1 plus 2t, y is equal to 1 minus 2t, and z is equal to 3 minus 2t. So here we're just using the equation for the line from chapter 12. So we have 1, 1, and 3 corresponding with our initial point here. And then we have the coefficients for t. We have 2, 2, and minus 2, or 2, minus 2, and minus 2, and those coefficients are coming from the components of the vector that we just found to be parallel with our tangent line. So the key for this problem is recognizing that the tangent line is going to be orthogonal to both the gradient of f. So the tangent line is going to be orthogonal to the vector that is normal to the cylinder. You can think about it coming out of the cylinder, as well as the gradient of g, or the normal vector to the plane that is defined by g. And for that reason, we know that the tangent line will be parallel to their cross product. So that's the key to this example. Okay, so now let's move on to a little bit of a different topic here. We're going to estimate change in a function in a particular direction. And to do so, we're going to use the directional derivative that we developed last time in section 14.5, and we're going to use it to estimate how much a function changes as we move away from a particular point, P naught, in some specific direction, so a direction that we specify. So to estimate the change in the value of a differentiable function f when we move a small distance, which we'll call ds, from a point P naught in a particular direction u, which we would specify, we use the following equation. So df, or the change in f, is equal to the directional derivative. So here, you remember from last time that the directional derivative is equivalent to the dot product of the gradient at the point P naught and our directional vector u multiplied by ds, where again, ds is going to be that small distance that we're moving from the point P naught. So let's give an example where we find this df. So we want to estimate the change in f of xyz is equal to y times sine x plus 2yz if the point pxyz moves 0.1 units from p naught, which is 0, 1, 0, straight toward the point p1, which is 2, 2, negative 2. So the direction vector is going to be the vector, or specifically the unit vector that goes from the point p naught to the point p1. So let's start out by finding that direction vector u. Well, u is going to equal the vector from p naught to p1 divided by the magnitude of the vector p naught to p1. So the vector from p naught to p1 will be equal to 2i plus 1j minus 2k, given here. And so now we just need to find the magnitude of that vector. It ends up being the square root of 9, which is just equal to 3. And then ultimately we can write down that the unit vector giving us the direction in which we're moving through the point P naught is given by u is equal to 2/3 I plus 1/3 j minus 2/3 k. And now we want to find the gradient of f. So we're going to take the partial derivative with respect to x, y, and z, and then fill in the appropriate components here. So when we take the partial derivative with respect to x, we get y times cosine of x. When we take the partial derivative with respect to y, we get sine of x plus 2z. And finally, when we take the partial derivative with respect to z, we get 2y. So this is our gradient here, and now we're going to find the gradient at our point P naught. So we plug in 0 for x, 1 for y, and 0 for z, and ultimately we get that the gradient at the point 0, 1, 0 is equal to the vector 1, 0, 2. And now, using this definition from above, we know that df, which is going to be an estimate of the change in f, is equal to the gradient of f at the point 0, 1, 0, dot product with our directional vector u, multiplied by ds, where ds is that small increment that we're moving. And so the problem gives us that ds is going to equal 0.1 units. And so we can just plug everything in that we just calculated. We get 102 dot product with 2/3, 1/3, negative 2/3, and then we're going to multiply the result of that dot product by 0.1. So this ends up being negative 2/3 times 0.1, or just negative 2/30. So that is the estimate of the change in f as we move 0.1 units in the direction given by the vector from P naught to P1. So in this next section, we want to generalize the idea of approximating a curve near a point using a tangent line. From Calc 1, the idea that I presented at the beginning of the video, to surfaces in space. So we're going to approximate the surfaces z equals f of xy at some point x naught y naught using a tangent plane as opposed to a tangent line. And ultimately we will call this a linearization of a function of two variables. So suppose that z is equal to f of xy is some differentiable function, and we would like to approximate the function near a point x naught y naught. What do I mean by approximate the function? I mean that we pick some other function such that when the point xy is sufficiently close to the point x naught y naught, then that other function that we've chosen is going to give us a relatively good estimate of what we would get when we plug that point into f of xy. So assume that we know the value of f of x naught y naught. We also know the partial derivative with respect to x and y at x naught y naught. Then if we move from the point x naught y naught to a point xy by increments given by the change in x, which is equal to x minus x naught, and the change in y, which is given by y minus y naught, then the definition of differentiability. So this definition for differentiability comes from section 14.2, I believe. I just briefly talked about it at the end. But the fact that f is differentiable gives us the fact that the function evaluated at xy minus the function evaluated at x naught y naught will be equal to partial x at x naught y naught times the change in x plus partial y of x naught y naught times the change in y plus epsilon 1 times the change in x plus epsilon 2 times the change in y. So this is just the definition of differentiability gives us this fact. And note also that epsilon 1 and epsilon 2 are going to go to 0 as the change in x and the change in y goes to 0. Basically all that's saying is that if we're looking at points x, y that are sufficiently close to x naught, y naught, this epsilon 1 times delta x and this epsilon 2 times delta y are going to be really, really small. And this ultimately gives us the approximation f of xy is approximately f of x naught y naught plus partial x at x naught y naught times the change in x plus partial y at x naught y naught times the change in y. So this approximation comes from the fact that epsilon 1 times delta x and epsilon 2 times delta y are going to be sufficiently small because we're assuming that the change in x and the change in y are relatively small, and then we can just add this f of x naught y naught to both sides of the equation up here, and that gives us this approximation here. So this moves us into the definition of the linearization of our function in two variables. So the linearization of f of xy at a particular point x naught y naught, where f is some differentiable function, is the function which we're going to call L for linearization. L of xy is equal to f of x naught y naught plus partial x at x naught y naught times x minus x naught plus partial y at x naught y naught times y minus y naught. So this approximation is exactly the approximation that's given right here, but we're now going to call this function L of xy. And we know that this approximation f of xy is approximately L of xy is going to be pretty accurate as long as our point xy is relatively close to the point x naught y naught. And this approximation will be called the standard linear approximation of f at the point x naught y naught. So intuitively what's going on here, and I do encourage you to look at some pictures in your book. I don't have a ton of pictures in this video here, but the book has a bunch of different pictures that that kind of describe geometrically what's going on here. We have a surface in space, and we have a specific point on that surface, and we're using the plane tangent to the surface that goes through that point to estimate our function, or the value of our function, as we move to other points away from the point that gives us the tangent plane. The same way that we did that in Calc 1 with that example that I gave at the very beginning of the video, where we can estimate the value of our function f as we move away from the point x0 by looking at a tangent line approximation. In this case, we just have a tangent plane approximation. Okay, so let's go into an example where we want to find this linearization of a function. So we find the linearization of the function f of xy is equal to x squared minus xy plus 1/2 y squared plus 3 at the point 3, 2. So to do so, we're just going to use the definition above and find the appropriate expressions to use that definition. So L of xy, this function L of xy, is equal to f at our point 3, 2, because this is x0, y0, plus partial x at 3, 2 times x minus x0 plus partial y at 3, 2 times y minus y0. So again, this is just using the definition of this linearization function that we gave above. And now we just need to find the appropriate values of these different expressions. So f at 3, 2, to find that, we're going to take 3 and plug it in for x in our function, take 2 and plug it in for y for our function, and we get 3 squared minus 3 times 2 plus 1/2 times 2 squared plus 3, and ultimately that will equal 8. Then we want to take the partial derivative with respect to x, and that ends up being 2x minus y. So again, if you're unsure, just pause the video here and make sure that my partial derivative is correct. The partial derivative with respect to y will be minus x plus y. Again, you can check that. And if we take the partial derivative with respect to x and evaluate at the point 3, 2, we ultimately get 4. And if we evaluate the partial derivative with respect to y at the point 3, 2, we get -1. And now we can take these values and just plug them back into the formula that gives us the function L of xy. And ultimately, after doing some algebra, once we plug some things in, we find that the linearization is equal to the function 4x minus y minus 2, which I have listed down here. So if we pick points that are sufficiently close to 3, 2, just to make sure that our approximation is going to be relatively accurate, we take those points that are close to 3, 2, and then we plug them into this function L of xy. The value that pops out here should be pretty close to the value that we would get if we took these same points, or the same point, and plugged it into our actual function. So f of xy is going to be pretty close to L of xy as long as we're looking at points that are pretty close to the point 3, 2. So after I've just spent some time talking about how this linearization gives us somewhat of a good approximation of our function f, the next question that we should naturally ask is, well, just how good of an approximation is it really? So in this next section, which is probably the most involved of the sections, we'll talk about finding bounds for the error of our approximation. So assume that we can bound, so we have some function f of xy, and just assume that we can bound all of the second order partial derivatives of f of xy. So we can bound this f sub xx, f sub yy, and f sub xy on some rectangle R centered at x0, y0. So what do I mean by that? I mean that the point x0, y0 is in the plane somewhere. Let's say that the point is right here. And there's some rectangular region centered at the point x0, y0, such that all of the second order partial derivatives, the absolute value, I should say, of all of the second order partial derivatives will be less than some integer m. So all of the second order partial derivatives are bounded by m. If this is the case, then we can actually bound the error of our approximation throughout this region R. So I'll label that rectangle R there. So the error is defined by e of xy, so the error at some point, is equal to the value we get when we plug in the point to f minus the value we get when we plug in the point to L. So this is just saying the error is the difference between the actual value of the function at xy and our approximated value of the function at xy given by the function L. Okay, and this leads us to this box that I have here. This is going to be an important box. If f has continuous first and second partial derivatives throughout a rectangle R that's centered at x0, y0, so remember that rectangle is represented pictorially like this. We have our point, we have a rectangle around it centered at that point x0, y0. And if m is some upper bound for the absolute values of our second order partial derivatives on the rectangle R, then the error of xy incurred in replacing f of xy on R by its linearization, where that linearization is this function L of xy, is going to satisfy the following inequality. And here we're going to give a bound for that error. So if these conditions are met, then we know that when we approximate using the linearization, we can only be this far off from the actual value if we were to evaluate f at the point xy. So the absolute value of our error at xy is going to be less than or equal to 1/2 times m, where m is that upper bound for all of our second order partial derivatives, multiplied by the absolute value of the change in x plus the absolute value of the change in y, all squared. And so this gives us an error bound, so we can know that our approximation is either going to be relatively good or relatively bad. And you can see if we want to guarantee that our error is really small, all we have to do is make sure that the absolute value between x minus x0 and y minus y0 are sufficiently small. Because if we make them really small, this equation up here, this 1/2 times m times x minus x0 plus y minus y0 squared, this whole right side of the inequality is going to get smaller and smaller. So we can be sure that the error is going to be small as we approximate for our function f. So at this point, we want to use this linearization from above to define a differential for the function f in two variables. So this differential is going to approximate the change in the function f as we move away from some point x0, y0. So to do so, let's start off by remembering some things from Calc 1, because ultimately we're just generalizing results that we know from Calc 1. So in Calc 1, if we have some curve y equals f of x in the plane, we defined the change in f as x changes from a to a plus delta x as follows. So we have the change in f is equal to f of a plus the change in x minus f of a. And we define the differential of f as df is equal to f prime of a times the change in x. And so the idea here is that the differential is going to approximate the change in f by using the tangent line at our point A, and this change in f that we give up here is going to be the exact change in f. So if we wanted to find exactly how much f changed, we would just take the point A plus delta x, plug it into f, and then subtract the function evaluated at the point A. So this differential df gives us an approximation of delta f. But now we want to generalize this idea to higher dimensions. So we consider the differential of a function of two variables. So we can let f of xy be some differentiable function and assume that both of the partial derivatives exist at some point x0, y0. Then if we move to a nearby point x0 plus delta x, y0 plus delta y, So here we have the change in x and the change in y. Then the change in our function f is given by delta f is equal to f of our new point, so f of x naught plus delta x, y naught plus delta y, minus f at our old point. So this makes total sense here. If we want to find the change in f, we're going to evaluate at the original point and then evaluate at the new point and find their difference. So if we want to find the change in L, where L is the linearization of our function f, then a little bit of calculation. With a little bit of calculation, we end up finding that the change in L is equal to partial x at our original point, x naught, y naught, times the change in x plus partial y at x naught, y naught times the change in y. And this leads us to the definition of our total differential here. So if we move from x naught, y naught to a point x naught plus dx, y naught plus dy, so these are just increments that we're moving away from x naught nearby, then the resulting change df is equal to the partial derivative with respect to x at x naught, y naught times dx plus partial y at x naught, y naught times dy in the linearization of f. So here we're specifically talking about L of xy, is called the total differential of the function f. So let's go into an example where we use the total differential to approximate the change in our function as we move away from a certain point. So suppose that we have a cylindrical can and it's designed to have a radius of 1 inch and a height of 5 inches. So that's the intention, that it would have a radius of 1 inch and a height of 5 inches. But the radius and height are off by a little bit. So the radius is off by plus 0.03 inches, and the height is going to be off by minus 0.1 inches. We want to estimate the resulting absolute change in the volume of the can. So to find an estimate for the change in the volume of the can, we're going to use this total differential that we just defined above. If we wanted to find the exact change, then we would take our new point, which I guess in this case would be 5 plus, or no, it will be 1 plus 0.03, and then 5 minus 0.1, and we would plug it into the equation that I have here for volume, and then we would subtract the volume when the radius is 1 inch and the height is 5 inches. But let's say that this calculation is relatively difficult to do and we just want an approximation. So we're going to use the total differential from above. So again, the volume of the cylinder is going to equal pi times r squared times h. That's just the formula for the volume of the cylinder. And now we're going to find the total differential. So we know that the change in the volume is going to be relatively close to the absolute value of our differential, or maybe I should say the absolute value of the change in our volume is going to be relatively close to the absolute value of our differential. And we know that the differential is going to be equal to partial r of v at r naught h naught times dr, where dr is the change in the radius, plus the partial derivative of v with respect to h at r naught h naught times the change in the height, which is dr and dh are both given to us in the problem statement above. So we want to find v sub r and v sub h. So we take the partial derivative of the volume with respect to r, and we get 2 times pi times h times r. And we take the partial derivative with respect to h, and we get pi r squared. And now we want to evaluate both of these partial derivatives at the point r naught h naught, which in this case is given to us as 1 inch for r naught and 5 inches for h naught. So 1 inch for the radius, 5 inches for the height. And v sub r will end up being 10 pi in that case. We can also evaluate the partial derivative with respect to h at the 0.15, and we end up finding that it is equal to pi. So now we can take both of these values, plug them back into our expression for the absolute value of the total differential here, and we get that it is equal to 10 times pi times 0.03 plus pi times negative 0.1, where again we've just taken dr and dh from the problem statement and plugged them in here. And at the end of the day, this is going to give us the absolute value of 0.2 times pi, and if you plug that into a calculator, it's approximately 0.63 inches cubed. So the change in the volume from the ideal cylinder, the cylinder that was, I should say the cylindrical can that was set out to be made with a radius of 1 inch and height of 5 inches, the change in the volume from that ideal cylinder or can to the can that was actually produced with a little bit of error is approximately 0.63 inches cubed, where we've just used the differential to find that approximation. And now finally we can move into the last section for this video. And in this last section, I just want to generalize the topics that we've talked about to functions of more than 2 variables. So specifically, we'll be talking about functions in 3 variables as opposed to 2. Everything generalizes pretty nicely. So the linearization of a function f of x, y, z at a point p naught, which in this case will be x naught, y naught, z naught, is given by L of x, y, z is equal to the function at the point p naught plus partial x at p naught times x minus x naught plus partial y at p naught times y minus y naught plus partial z at p naught times z minus z naught. So the only difference here is that the linearization will include this additional summand here where we use the partial derivative of z at p naught. The second thing to note when we're generalizing to functions of 3 variables, we want to generalize our error bound. So suppose in this case that R is a closed rectangular solid that contains the point P naught. So remember from before, we had that rectangle R that was enclosing our point in the plane. In this case, we're going to be talking about a point in 3 dimensions, and I'm already sure that this drawing is going to be pretty bad. But let's say that we have some point in 3 dimensions, which I'll draw in red here. Then we're going to be talking about a cube, basically, or a rectangular prism that is containing that point. Hopefully something like this. Yeah, that's not too bad. So in this case, we're going to be talking about a closed rectangular solid that contains our point P naught in space. And inside of that closed rectangular solid, we have that the second order partial derivatives of f are continuous. And suppose also that all of the different second order partial derivatives are going to be bounded by this number m throughout the rectangular region R. Then the error is defined to be the value of f at the point xyz minus the value of xyz when we plug it into our linearization. And that error is going to be bounded as follows. So the absolute value of the error is less than or equal to 1/2 times m times the absolute value of x minus x naught plus the absolute value of y minus y naught plus the absolute value of z minus z naught, all squared. And here the only difference is that we had to account for some more second order partial derivatives when we find this bound m, and we also add in this additional absolute value of z minus z naught. But other than that, the bound for the error will be the same. And finally, if the second partial derivatives are continuous, and if x, y, and z change from x naught, y naught, z naught by small amounts, which we'll call dx, dy, and dz, then the total differential is defined to be df is equal to partial x at p naught times dx plus partial y at p naught times dy plus partial z at p naught times dz. And this differential is going to give a good approximation of the resulting change in f, delta f, of course, as long as the point x, y, z is relatively close to the point x naught, y naught, z naught. Okay, so now we can go into the final example for this video here, just an example where we apply some of the things from before to a function with 3 variables now. So the first part of the example is to find the linearization L of xyz of our function f of xyz is equal to x squared minus xy plus 3 times sine z at the point x naught, y naught, z naught is equal to 2, 1, 0. And then the second part of the example will be to find an upper bound for the error incurred in replacing f by L on the rectangular region that is given by the absolute value of x minus 2 has to be less than or equal to 0.01. The absolute value of y minus 1 has to be less than or equal to 0.02. And the absolute value of z, or you can think of it as z minus 0, taking the z coordinate from this point here, has to be less than or equal to 0.01. So these 3 different things here that I've just drawn green under, these 3 different conditions are going to define a solid rectangular region in space. And basically what this is saying is that the x-coordinate can't be more than 0.01 units away from the x-coordinate of our point P naught, which is 2. That's what we have. The absolute value of x minus 2 has to be less than or equal to 0.01. And the same can be said for y minus 1 and z here. So ultimately, these conditions are just defining that solid rectangular region around the point 2, 1, 0. So let's get into the solution for this example here. So the linearization L of x, y, z will be equal to f at p naught plus partial x at p naught times x minus x naught plus partial y at p naught times y minus y naught plus partial z at p naught times z minus z naught. So this is just using the definition of that linearization from 1 here that we've generalized to the function of 3 variables. And so now we need to figure out all of these different values to plug back into the equation for the linearization. So f at the point 2, 1, 0, to calculate that, we take 2, plug it in for x, take 1, plug it in for y, and take 0 and plug it in for z into our original function given up here. And we end up finding that f at the point 2, 1, 0 is equal to 2. Now we can find the partial derivatives with respect to x, y, and z of our function f. So the partial derivative with respect to x is equal to 2x minus y. With respect to y, we get minus x. And with respect to z, we get 3 times cosine of z. Again, if you want to check those, you can just pause the video and make sure that the calculations are correct. We're just taking the partial derivatives or a function f. And now we can take the point 2, 1, 0 and plug it into each of these partial derivatives. When we plug into f sub x, we get 3. When we plug into f sub y, we get minus 2. And when we plug into z, we again get 3. And now we can take these values and plug them back into our expression for L of xyz. So I'll pull that up here. L of xyz will then equal 2 plus 3 times x minus 2. So the 3 is coming from here. And this minus 2 is coming from the x-coordinate of our point. And then we have minus 2 times y minus 1. Again, the minus 2 is coming from here. And the minus 1 is coming from our point up here, plus 3 times z minus 0, where the coefficient there is coming from the same place. And if we simplify, we can find that the linearization L of xyz is equal to 3x minus 2y plus 3z minus 2. So that answers the first part of the example here. We found the linearization for the function f at the point 2, 1, 0. And now we want to find our upper bound for the error that is incurred when we replace the function f by L on that given rectangular region from above. So remember that the error is defined to be the value that we get when we plug x, y, z into f minus the value that we get when we plug x, y, z into our linearization L. And we also know that the error will be bounded by, or it will be less than or equal to, 1/2 times m times this x minus x naught plus y minus y naught plus z minus z naught squared, where m is a bound for all of the second order partial derivatives over the given rectangle R. And x minus x naught, y minus y naught, and z minus z naught are all maximized in that rectangle. And you'll see what I mean by that when we get down to the bottom here. So the first thing to do to find our integer m is take all of the second order partial derivatives. So you can just take my word for this if you want to. The partial derivative with respect to x, or the second order partial derivative f sub xx is equal to 2, f sub yy is equal to 0, f sub zz is equal to minus 3 times sine z. This is probably the most interesting one out of the 6 that we find here. F sub xy is equal to minus 1, f sub xz is equal to 0, and f sub yz is equal to 0. Now you might be saying to yourself, if we're taking second order partial derivatives with respect to 3 different variables, shouldn't there be 9 second order partial derivatives that show up? Because what about the partial derivative f sub yx as opposed to f sub xy, and f sub zx as opposed to f sub xz? Well, because we have assumed that our partial derivatives are continuous, we can use a condition that we developed, I think, in section 14, section 14.3, that tells us that the mixed partial derivatives are going to equal each other regardless of the order that we take the partial derivatives. So that means that f sub xy is going to equal f sub yx, and f sub xz is going to equal f sub zx, and so on. So we really only have to check these 6 here. But anyways, so we have these 6 different second order partial derivatives, and we want to find an integer that bounds all of these partial derivatives over the rectangle R that is given to us. So right off the bat, we know that m is going to have to be greater than or equal to 2, because this second order partial derivative is equal to 2 everywhere inside of the rectangle. But now the question is, does 2 also bound all of the other second order partial derivatives? Well, 2 is clearly going to bound this one, this one, this one, and this one, because 0 and minus 1 are both less than or equal to 2. So the last question we need to ask is, does 2 bound this guy here, f sub zz? Well, inside of the rectangle that we're talking about, notice that the absolute value of z is going to be less than or equal to 0.01. So if we take a point from inside of that rectangle and we evaluate this second order partial derivative at that point, we know that z is going to be less than or equal to 0.01, right? Yes, less than or equal to 0.01. And in fact, that means that the absolute value of f sub zz will be less than or equal to 3 times sine of 0.01, which is approximately 0.03 over our rectangle. So it's just that region R that we're talking about. And because 0.03 is, of course, much less than 2, we can let m equal 2. So m will be a bound for all of our second order partial derivatives here over the rectangle. And now we can plug back in for the expression that gives us the upper bound for our error. So the absolute value of our error is going to be less than or equal to 1/2 times m, which is 2 now, times the absolute value of x minus x naught, which is actually just given up here in all of these conditions. So again, 2 is x naught, 1 is y naught, and 0 is z naught. So this region is telling us that the absolute value of x minus x naught is going to be less than or equal to 0.01. And the absolute value of y minus y naught is going to be less than or equal to 0.02. And likewise, the absolute value of z minus z naught will be less than or equal to 0.01. So we can just take those three values and plug them in here for x minus x naught, y minus y naught, and z minus z naught. And now we can just evaluate this expression. So ultimately we get 0.04 squared, which ends up being 0.0016. So as long as we are looking at points inside of that rectangular region R, we can use the linearization to approximate our function f, and we can be sure that the error that we get when we use that linearization is going to be less than or equal to 0.0016. So the approximation is going to be pretty dang good inside of that rectangular region. Okay, so that is the end of the material for section 14.6. There is homework for section 14.6 that I've already posted on Blackboard, so feel free to get started on that. I think it's due on Friday, if I remember correctly. And then just look forward to section 14.7, the last section for chapter 14.